In the past 2 weeks, we studied the data plane in the network layer. Now it's time to study the control plane, which is the brain of the network. So these are the things that we are going to discuss. We are going to talk about just like the principles of the control plane. What do we mean by routing algorithms, different types of routing algorithms, and we will just like go over some of the widely used routing protocols, techniques that we mostly use. So let's just like go first with the routing protocols. What kind of routing protocols do we have? So we can categorize the routing protocols into two types, which is either to be a link state routing protocols or distance vector routing protocols, and we will learn in depth how each of these category is working. Okay, so let's just like get started with the link state. So in general, before we get started into one of these protocols or these types of protocols, let's just like have some definitions. So the first thing, which is when we are trying to send the data from, let's say, from here, let's say to this machine here, we have to define main things, which is what is the source and what is the destination, right? In order for us to do any communication. Another thing which we don't define, but the core network devices is defining, which is the path. The path, or let's say, what is the best path for our packet to transmit from the source to the destination. So this is not defined by the user. The path is something defined by the network device like the routers. Okay, so we can define the path as a sequence of routers that we can just like transmit our data from the source to the destination. So different routing protocols has different metrics or different way of working. So some routing protocols, they will just like see how much does it cost to move from here to here. Another protocol may discuss, or let's say will just like have the fast is the main objective. Another routing protocol would make the least congested path is the best path for just like your data to be transmitted from one end to another end. So to just like define good, we have to say what kind of good are we looking for, or we have to define good by itself. So is it good in terms of cost? Is it good in terms of fast? Is it good in terms of network congestion? Okay, and by the way, routing is considered as the top 10 networking challenge, which means it's not an easy job. There are many and many routing protocols that it's just like in the academia and the research, it's all mentioned there, but the ones that we just like are going to discuss is just like the ones that is widely adopted. So in any network, we can define our network as a graph. Okay, we can visualize it as a graph. So in a graph, always we have two key components there. The first one, which is the nodes, which is in this case are the routers, and the edges, which is in this case the link between two routers. So in graph, always we have something called node and we have something called edge. In this case, the node here is just like the routers, right? As we can see here. And the edge is the link between two nodes, which is in this case is going to be, we can call this as an edge because it connects X to U. So here, if you ask in the exam, for example, define the nodes, then the nodes in this diagram here would be U, V, W, X, Y, and Z, right? And the link, you have to mention all the links in this way. So here, the first link is from U to V, from U to V, let's say this one. This is number 1, right? Then from U to X, this is number 2. From V to X, this is number 3. So these are the edges that we have in our network. So you have to be aware of these things, of these concepts. Node is just like the routers. The edge is the connection between two routers. Okay? The other thing that you have to understand, which is the cost. Most of the time, the notation is going to be something like this. So the cost, which is C here, from A to B. Okay? So the cost from A to B, this is the representation here. So we can say that the cost from W to Z, or we can say C from W to Z is equal to 5, right? This is if you have a direct connection between W and Z. But what if you are trying to access to some nodes that is not a direct connection? So for example, let's say from W to U, okay, from W, let's say from W to U. This is a none, right? So you have no idea how to access, unfortunately no. We have a link here between W and U. Let's go with U and Z, as what we mentioned here. C, U, and Z. Since there's no direct edge or direct link between these two, so at certain point, you will have infinity here. So the infinity here means you have no direct connections. So here, the cost from W to Z is 5, because we already have an edge that costs 5, right? On the other hand, from U to Z here, there's no direct connections. Therefore, at this specific time, we can say that the cost is infinity, because, or we can say it's unknown. But just like we wanted to give some numerical representation, therefore we are using infinity here. Okay, so whenever we have any routing algorithms, the way that we define the routing, we have two ways. So most of the time, either we have something called a global, which all the routers will have just like a complete topology. They are aware of the whole topology of the network. Okay, and this kind of routing algorithms is called link state. The other type, which is the distance vector, which means at first or at specific time or at the start, always the router will be aware of the neighbors only, and the divergence, or just like then by just like in an iteration way. So let's say at the start, let's say at t equal to 0, for example, U here will be aware of V and X. At t, which is time or time step number 1, I will be aware of the others at this point. At t2, I might be aware of the whole network. That means the availability or the visibility of, let's say, to one router from another router, it depends on how big is your network. Okay, so this is not, each node doesn't have a whole or a full topology of the network. Okay, so this is the first way to categorize the routing algorithm. Another way to categorize the routing protocols is through whether it's static or is dynamic. Okay, so static means administrator or the admins of the network are the ones who's going to define how to, just like let's say, to go through one path. So for example, let's go with the static here. If you are an admin and you want to define a path from one router to another, then always you can just like use the static here. And in the static routes, you are telling, or you are forcing the packet to be forwarded through one packet no matter what. So for example, you are saying that if you want to go to, just like from U, let's say from U to W here, we already have a cost of 5, right? But we might have another alternative which might be less. So in this case, if we go through U, X, then 3, let's say this path here, U, X, and W would be 4, right? So if you are using some dynamic algorithms there, for sure this one is going to be picked because it's more efficient. But when you are using static, you would say, I don't care how efficient this route will be. I just like wanted to have anyone wants to go to W from U should go with this path. I will not consider this one. So this is the meaning of the static. That means the router or the routes will be defined by the administrator, and the router has no rule in terms of defining or computing what is the best route to move from one end to another end. In most cases, the static ones or the static routes is something, or we use it when we don't expect a huge change in our network, or the changes in our network is not that fast. Okay, but on the other hand, if we just like use the dynamic, which is the ones that we are using in our internet nowadays, is completely updated or completely changed based on the criteria or the routing algorithm that we are using. So for example, in this case, maybe we don't have let's say this link. Let's pretend that we don't have this link. Okay, and now we have, if we want to move from U to W, the router will learn by itself that either we have one link which has 5, we can go from U to W with the cost of 5, or we can go to from U to V to W with the cost of 5, because 2 here plus 3 is 5, right? And we can go through just like X, we can go with 1, 2, and 3, which is in this case, we can go from U, X, and V to W, which is in this case going to be 6. So in our case here, since we have both of them are less, then we might have something better, right? Okay, now let's go with the other one, which is U, X, Y from here. Let's go with this from this link. So this one is going to be less, right? X, Y, W, which is in this case going to be 4, right? Or 3. So here 1, 2, and 3. So always the dynamic is gonna do the calculation by itself. So there is no control from the administrator. And in our network nowadays, we are mostly using the dynamic routing protocols because we might have this link today, but we might not have the same link tomorrow. So the links or the edge between the routers is changing. Therefore, we are using, most of the time, we are using the dynamic routes. Okay, another thing that I want you to just like understand, most of the time when you are using, or just like the static route. Hold on, let me go back. So let's go with the pen here. So when you are using the static route, always you will have to define all the nodes. So let's say if you want to define from U to Z, you have to define the next hop. So in this case, you'll define, let's say, from U to W. Then once you're done with U here, you will have to go to W to define a path or a route from W to Z. So always you will just like do one let's say hub at a time. On the other hand, here on the dynamic, you don't need to do anything because each router will just like compute the routing table internally, then share it with their neighbors. And the same thing is going to be done here. So let's go. If we are at V is going to calculate the routing protocols and it's going to share it with W and with U and with X. The same thing here with X. They're going to compute their network, or let's say their routing protocols, and share it with V, U, and Y, and W. So most of the time the dynamic is going to be calculated internally and then share these calculations or computations with the other, or share the routing tables with the neighbor routers. So let's go first with the first algorithm that we are going to learn about, which is the Dijkstra link state routing algorithms. So this protocol or this algorithm is centralized. Okay, that means each node or each router is fully aware of the whole topology of the network. Or on another words, we can say that the cost from each node to any other node within the network is already known by everyone. Okay, and this task is accomplished by the link state broadcast, and most of the time, if not all the time, all the nodes have the same information. Okay, so let's try to just like set up some notations to be sure that we are understanding. So always whenever you see something like C from X to Y, that means this is the cost for you to move from X to Y. That means always there is a direct link cost from X to Y. If you have no direct cost, or let's say no direct link, that means the cost would be infinity. Okay, so dV here, which is the distance or the estimated cost or the estimated distance from one end to another end, this is always, as you can see, estimated. So dV is always meaning to estimated. PV here is the predecessor of the node along the path, so from where you are coming. Okay, and this is just like the n prime here means the set of nodes whose least cost path definitely known. So let's just like get started with, I'm not gonna go through the algorithm, you can just like go over it, but I think it's better for you to go through just like one quick example. So first, always let's just like say that we are going to start from U here. Okay, so this is our starting point. We wanted to know how to access all these things. Okay, so the way it's working is you will write down the cost of each edge that has a direct link from the source to the destination. So at this point, the edges that we have edge from U to W, and from U to V, and from U to X. Therefore, you will have to just like to write the cost for each direct link. So here we can reach to V at the cost of 2, and this is through U, right? And we can access from U to W with the cost of 5, right? And we can access to X through U, which the cost of 1. So at this point, do we have access to Y or Z? Since we don't have direct link between Y and Z, therefore we are saying it's infinity, right? So now this is the first step for you to understand the whole topology, right? After we finish the first step, we will go through the least cost. We will pick for the next step, we will pick the next step which has the least cost. At this point, we have X with the cost of 1. Therefore, we will start to go with X. So as you can see here, U, then we just like wrote down the X. So now from X, now you are just like done with here, and you are standing here right now at X, right? Now let's just like see how much does it cost me to come from or to move from X to V, right? As you can see, the cost here is 2, right? But don't forget, this is always, the students forget about this, which is how much did it take you from U to X, which is in this case 1. So most of the time you will have to just like combine these two together. So the cost it gets you from U to V through X is 3, right? Because here 1 and here is 2. So now we know the cost from X to V is 3. But I already have 2 here, so I don't need to go through this, right? I don't need to update it anymore. The reason for that is I'm looking for the least cost. So I am only going to update my table, the table, if I have less cost. This is the only way it's working. So now we know if we move from U to V through X is going to be 3. But I already have a direct link that give me 2, which is less, right? Therefore, I'm just gonna stick with the least amount, right? Now, from X, I can go to W, right? So the cost here is going to be 1 plus 3, which is 4. Before, we had just like from U to W with the cost of 5, right? And as you can see, now we can have another path to W, but with least cost. Therefore, we are going to update it now, which is going to be 4. So X, since I'm at X, I don't need to write anything down because it's already explored, right? Now, from X to Y, it's going to be 2 because 1 plus 1 is 2. And 2 less than infinity here, right? Therefore, I can arrive to or go to Y from U through X with the cost of 2. So can I go from X to Z at this point? As you can see, there's no direct link, right? Therefore, I'll just like leave it as it is, which is at this point infinity. Now I'm done with the second step. Now I would go with the least number, right? Which is now I can either to go with Y or V, right? So at this point, I'm gonna go with Y, for example. Okay, In many cases, in your just like in the test, I would tell you if you have just like two equivalent costs, then you would go, for example, with alphabetic, for example. Okay, so here I can go through X through Y, from X to Y, right? Which is going to be 2 at this point. Now I will move from here to Y, right? Now I'm standing here. I already know the cost it cost me to move from U to Y is already 2, right? So now I'm gonna go from Y. Can I go from Y to V? No, right? As you can see, if I cannot, then I will leave it as it is. Now, can I move to W? Yes, I can move from Y to W, right? And the cost here would be 2, and 1 here is 3. 3 is less than 4. Therefore, I'm gonna update my routing table at this point, because I can access or arrive to W through U, X, Y with less cost, right? So now I already investigated X, I already investigated Y. Now the least amount here, or the least cost, is V, right? Which is at this point is going to be 2. Now I'll be investigating this, which is V. So to move from V to W is going to be 2 plus 3, which is 5, but I already have 3, so I don't need to update it, right? Is there anything else that I can update? Most of the time, it's not gonna be anything to update. So at this point, I already investigated V. Now I will end up with 3 values here, which is either to go to Y 3 or 4, right? At this point, I will go with the least cost, which is at this point, which is going to be W, right? So now we are at W here, right? And we know to reach to W, the cost is 3. And the cost from W to Z, 3 plus 5 is going to be 8. So it's not less than 4, right? So I'm gonna stick with what I already have in there. Now the last one, which is going to be the 4Y here, right? And you're gonna take the Z at this point. As you can see, this is just like gonna give you the whole thing. So now everyone in our routers will have almost the same routing tables. That means if you want to move from one place to another, then you will be aware how much it's gonna cost you for each one of them. And just like one note here, let me try to delete all these things. One thing to notice here, which is most of the time you will be encountering some definitions or terms, something called explored and something called discovered. So this way, or these terms, is really useful when you are working with Dijkstra algorithm. So the first thing, if you are standing here, that means you already discovered this one, but you haven't explored what are the outputs or the outlinks. Once you're done exploring the outlinks, that means it's already explored. You don't need to explore it anymore. You will move always to the next least cost from, so if you are standing here, always you will be moving to the next least one. right? So this is always the case that you want if you want to go. Now, since you're already done with all these things, now you can write down any path that you want. So let's go with, if you want to move from U to V, right? You know that the least cost for you is 2, right? Therefore, you are using this one. Now, if you want to move to, let's say, X, you know that U to X is going to cost you 1. Now, if you wanted to move from U to W, you know it's going to cost you 1 and 3, which is 4. And always, as you can see, if you wanted to just like see what's going on, always you can, sorry, it's going to be 3 here, because we can go from here, here, and here. And always, the number that you're going to get is, you read it this way. So the last thing that you have here. So 3 through Y. So you can arrive to W through or via Y with the cost of 3. Right? So another way to do it is, let's say if you want to just like get the path from U to Z, right? So most of the time, the way you're gonna do it is you're gonna stand here and just like go backward, right? So now you are at this step, you know that you'll have to go backward to Y, right? Then from Y, you are going to go X, as you can see, X, then you will go back to U. So either one, it should be easy for you to just like to tell what's going on. So these are just like the resulting least cost path for the whole thing that we want. So the forwarding table, or the things that we are going to exchange with our neighbor, right? So this was done on the U, right? So the destination to V, you can just like go from U to V. The destination to X is going to be from U to X. The destination to any other nodes, which is W, Y, and Z, is going to be through X. So this is just like the outgoing link. So this is going to be here exchanging with the neighbors here. Now, if you come here, let's say, if you want to get the routing table from just like X, it's going to be the same thing. So from X to U, let's say from X to V is equal to 1, right? Sorry, from X to V is going to be 1, 2, and from X to U is going to be 1, and from X to W is going to be 3, or always you're gonna say the next hop here. So let's just like do it this way. So let's go with X to V is going to be X and V, right? And from X to U, it's going to be X and U. And from X to Y, it's going to be X and Y. From X to W is going to be X and Y. And from X to Z is going to be X and Y. As you can see, always you are going to just like go, what is the next hop this is the thing that it's done. If you just like here at U, if you want to move to V, then you will go from U to V. If you want to go to X, then you will go with UX. But if you want to go to W or Y or X, then always just like go to the next hub. So the forwarding table that you have always is going to be having the next hub. It's not going to have everything in your network. Okay? So this is another example. Let's just like do it real quick. So in this example, let's go from U to V with the cost of 7, right? So always you're gonna go with the direct links. So the direct links from U here is X, W, and V. Therefore, there is no direct link from Y or Z, right? Therefore, Y and Z is gonna be infinity here. So the cost from U to X is 5, from U to W is 3, and from U to V is 7. Now you're done with the first step here, right? To move to the next step, which is step number 1, you will pick the new least cost here, which is 3 at this point, right? Therefore, it's just like W here. Now, you will be moving from here to here. This is number 1 now. So this is 0, and this is number 1. Now, you will just like calculate again. Always do not forget the cost that take you from the previous one to this one to be added to the new link. So now let's go from W and V and Y, right? So from W to X, I already came to 3 and 4, which is 7, but I already have 5. Therefore, I don't need to update it because I already have the shortest path here, or the least cost path, right? Now from W to Y is 8. 3 plus 8 is going to be 11, right? 11 is better than infinity. Therefore, now we can arrive to Y through or via W with the cost of 11. Now I'm done with this area here, right? I'm gonna go now to the least number or the least cost, which is X. Now I'll be moving from here. This is step number 2. Now I'm moving here, right? Why? Because X from U to X was the least one or the least cost. So right now I'm here, right? Now let's go with the direct ones. I can go to W, which is 5 plus 4. But W here is already 3, so it's just like its minimum. I don't need to update it. I can go from X to Y, which is 5 plus 7, which is going to be 12. And I can go from, as you can see here, you can arrive to Y with the cost of 12, but you already have the cost of 11 from U, W, Y, right? So you don't need to update it. Now let's see Z. You can go from X to Z with the cost of 9 and with the cost from U to X as 5, so it's going to be 14. So 14 is going to be better than, as you can see, better than infinity, right? Now you have all these things. Now what is the least? Now the least is V, right? So the V, or the cost to V, is going to be from U to W and from W to V. This is the cost of 6, right? And let's say this is step 3. So right now we know to move from V to Y is going to be 13, right? Because it's going to be 10. 3 plus 3 plus 4 is going to be 10, right? So I can arrive to Y with the value of 11. So here is less. Therefore, I'm going to update it now. As you can see, I already updated here to be 10, right? Because 3 plus 3 plus 4 is going to be 10, right? And since I have no direct access to Z, therefore I don't need to update it, right? Now, the least that we have here is 10. So we are going to 10 now, which is at this point Y. So this is number 4 now, or step number 4. Now I can arrive to Z with the cost of 2 plus 10, which is going to be 12, right? So 3 plus 3 plus 4 plus 2 is going to be 12. Therefore, now I can update, because the previous one was 14 through X. Now I can get through Y with the cost of 12, right? So now we can just like verify the way it's working. So always, the key concept here is always go from just like the starting point to the direct edges or the direct nodes. This is the first thing. Once you discover or explore the whole thing, then you will move to the least cost. This is going to be your next step, as what we saw here. We start with 7, 3, and U, which are the edges from U to X, from U to W, from U to V. Then we picked the least cost, which is 3 at this point. Now you will be investigating from here, and you will do the same thing. Then you will go with the least cost until you discover the whole or explore the whole network. The second category of routing protocols, which is the distance vector. Let's see how does it work. So the distance vector algorithm is based on Bellman-Ford equations, which is mostly we call it as a dynamic. Let me pen, which is called or based on dynamic programming. So the way it's working is, let's say if we have these nodes here, and let's call this one 1, 2, 3, and 4. Each one of them, let's just like make this connection here this way. Each one of these nodes will calculate the distance to its just like neighbor. Let's make one more like this. So it's going to be something like this. So here at 1, it's going to calculate from 1 to 3 and from 1 to 4, right? And we can call this from 1 to 3. Yeah, let's just like keep it this way. This is number 1. Number 2 is gonna do from 2 to 3, right? Number 3 here is going to go with 3, 1, and 3, 2, and 3, 4. Number 4 here is going to do 4, 1, and 4, 3. So each node is going to do its own calculations on its own. Okay, then this calculation is going to be used by other one. So for example, let's say I'm standing here and I want to get to know how to get to number 4. Okay, so I already know how to get number 4 from 3, right? So all I have to do is just like calculate this area here, and I don't care about this because it's already calculated. So I will add up the calculation here to the calculation here, but I don't need to just like go from 2 to 3, 3 to 4, because 3 and 4 it's already calculated. So the same thing here, dvy, for example, here is something already calculated. That's why we call it dynamic programming. You don't need to just like do it all from one end to another end. So you will do it just like from one end to the next hub, and from the next hub it's already calculated to the other next hub. So the way with just like Bellman-Ford equations is doing, so let's pretend just like say that we have x and y. We want to get the least cost path from x to y. Then we will go from just like we will pick the minimum value from v, and we will just like say from x to v here. Let's say this is x, and this is v, and this is y, right? And this is the connection here. So from x to v, let's say this has 1, this has 3. Okay, so here we are going to go with x to v is 1, and from v to y it's already calculated before, which is going to be 4. So at this point, since we already just like we have one link, therefore we cannot just like go with the minimum. It's just like this is going to be the minimum value. But if we have multiple links, then we will have to consider the minimum value. Okay, so let's just like go and check this one. So right now, let's say that the value to get to z from v is 5. Okay, this one is already calculated here on v, and on x it's calculated that to get from x to z it's gonna cost you 3. And the same thing on w here, it's pretty calculated that to get from w to z is gonna cost you 3. Okay, now we want to just like know what is the distance or the cost to get me from u to z. So right now at u we have no idea where z is, but since we are sharing, or we can see, or there's some exchange in terms of the values or the distance vector tables, we'll be able to get it. So the way it's working here is we're going to take the minimum value of, now we want to go from u to z, right? The first thing to do is to go with the direct link to the u, right? So the direct link is from u to v, u to x, u to w. Therefore we have all these things here, u to v, u to x, and u to w. Now since let's just like go with the first one here, we moved from here to here. Now we already know that the distance or the cost from v to z is 5. From v to z is 5, right? Then we calculate the same thing. We'll move from here to here. From x to z, it's already calculated before, which is going to be 3. The same thing is going to be from w, which is here, to from w to z. So it's pretty just like straightforward. So here from c u to v is 2, plus from V to Z, it's already here, is 5, right? So this should give you 7. Now, let's go to the second one. From U to X, the cost is 1, and from X to Z is already there, is already 3, right? So it's 4. Now, from U to W is 5, and from W to Z is already mentioned there, is calculated, which is 3. So at this point, it's 8. Now, since we have 3 entries here, we'll take the minimum value. At this point, this should be the minimum value, right? So now, if you can, it's going to be almost the same thing. Therefore, du to z is going to be 4, right? So now we pretty much know what is the key idea. So the way it's working is, from time to time, each node sends its own distance vector estimation to the neighbors, or the one that has direct link to it. Okay? Whenever you receive it, so if you don't receive any update, then you should be fine. But if you receive an update, then you will have to do some computation to decide whether you should change your distance vector, or your distance vector what you have is the best you could. Okay, so let's just like see how it's working. So each node is gonna do distance vector table, each node or each router. Okay, then once it's done, it's gonna wait for the change in local link. If there is any message coming from the neighbor, whenever you receive a message of the change, then you will do recompute. So at first, initially, you will do your own table. Once you have just like a new message or update message from your neighbor, then you will recompute your distance vector table based on the update that you receive from your neighbor. Okay? If there is any update on your calculation after your computation here, then you'll notify your neighbors that this is my new distance vector, and this is going to happen for each node or each router in your network. As you can see, this operation is going to be iterative and asynchronous. So each one is going to work in his own. There is no synchronization between the routers. Whenever one router has any updates, it's going to broadcast it to the neighbors. Okay? So now we can say that distance vector algorithm is distributed because there's no central place that is going to calculate everything. Everyone's going to, just like every router is going to calculate its own distance vector table. Okay? So let's just like take this example here. So at T0, which is the initial phase here, each router here is going to calculate its own DV or distance vector. So the way it's going to be calculated is, you will mark the cost of each edge here, which in this case the direct edge between this router and your neighbor. So from A, to move from your, just like from A to itself, it's going to cost you 0, so there's nothing there. To move from A to B, it's going to cost you 8, right? To move from A to C, is there a way or a direct link between A and C? There's no direct link, therefore you will add infinity because it's unknown. For you, it's not feasible to you from here, okay? Because in distance vector, you can only see one hub or your next hub. That's it. From A to D is going to be 1, and the remaining, since there's no direct link, it's going to be just like infinity. So this is going to be at t0, right? Let me try to delete. So this was at t0. As what I mentioned before, all the nodes are going to do their own distance vector, right? Then this distance vector is going to be shared with your neighbor. As you can see here, A is going to share its distance vector with B and D. And the same thing for B is going to share it with A, C, and D. So it's going to have just like broadcast to your neighbor. Each one in your neighbor is going to receive this distance vector. So now, as you can see, at T1, each of these routers receive a distance vector from the neighbors. Once you receive it, you're going to do compute. You're going to do the computation based on your just like distance vector and the received distance vector, if you have any updates or not. If you have no updates, then that's fine, you stop there. But if you have an update, then you will update your distance vector and then send it, or send the new local distance vector to your neighbors. So the way it's working here is, if you have update, if there's update, then you would do share. Else, do nothing. If there's no update on your distance vector. And this is the case for just like for well-established network. Most of the time you won't find all of them is going to be working. Some of them which has some changes in the link, or there's no connection between the routers, or the connection dropped, then you will see some changes. But other than that, it's not going to be a problem for you. So you only notify your neighbors whenever you have some update. Okay, you will do the same thing. So this is the iterations. For each iteration you're gonna do the same thing. Now let's just like try to do one example here. As you can see, this is distance vector at A, distance vector at B. As you can see, each one of them has its own data. So let's say that you are at B here and you want to do the computation. How does the computation is going to be done? You will be receiving from A, from E, and from C. How are you going to do the calculations or the computation? So now you are having 3 tables here, right? This is 1 and 2 and 3. And you wanted to see which one has the least cost, so you can reflect it into your distance vector, right? So let's just like go from just like B to A. So let's take it one by one. If you wanted to move from B to A, you already know that in your table is 8, right? From B to A is 8. And you already know in the distance vector of A, or the table that coming from A, you know from A to A is 0, right? Therefore, this total is going to be 8. Now, let's check. We already done with A. Now, let's go with C. You know from C to A is infinity, right? And here, you know from your, you know it's 1. From B to C, right? You know it's 1, so this should give you an infinity value. The same thing from B to E is going to be 1. And from D, now you are going to check from D, E to A. From E to A is infinity, right? Therefore, it's going to be infinity. Now you will take the minimum value. In this case, it should be 8, which is the one that you have here. So there is no update to the route or the path from B to A. Now let's go with the second one, from B to C. So we're taking the second one. Now let's try to see from B to C. This should be C. From B to C, from A to C here, from table A to C, from A to C is infinity, right? And from B to C is already 1, right? Therefore, you will end up with infinity. Now, from B, C, okay, and you want to get the information from distance vector of C, from C to C. So this is C, from C to C is 0. And you already know from B to C is 1, right? So 1 plus 0 is 1. Now you go from the same thing, from B to E. So this is from E to C. Let's take it from here first. From E to C, this is infinity, right? And from B to E, you already know that from B to E is 1. So this should give you infinity. Therefore, now you will end up with 1 because you are going to take the minimum value. So now from B to C, you know it should be 1. So it's the same thing. So you don't need to update anything at this point. You do now the next one, which is D. Now you will go from B to A, right? So this should be 8 from B to A because it's already known by my table here. And from A to D, as you can see, from A to D here is 1, right? Therefore, it's going to give you 9. And the same thing is going to do to the next one. From B to C is 1. From DC, which is here, to D is infinity. From DC to D is infinity. Yeah, there's something wrong in here, right? I think, yeah, there's something wrong. Let's just get back to it. So from B to E, I already know it's 1 in here. And from E to D is 1. This should be infinity, and this should be 2. So this is how it goes. So one thing to notice here, which is how to read all this information. So anytime this is the source, this tells you what is the start point of your distance vector here. So here the distance vector from B to A is 8, right? Now D and this one, the small one here, this tells you to which distance vector we are looking for. So here dA, that means you will have to go and check this value within the distance vector of the node A. The same thing here, from B to C, since you already have here B, that means you are trying to see the value from B to C. From B to C is 1. Now DC here, that means the value, or this value that you are trying to get, you can get from the distance vector table on C, right? So DCE, so DCE here should be infinity, right? The same thing here, BE, that means from distance vector of table of B, you will take the distance to E, right? And from the distance vector of table of E, which is this one, you will get how much it's going to take to E. And you will continue to do the same value. So now, once you did all these calculations, and you just like picked the values, as you can see here, now we will update. So this is the results of your computations. This is your computation, and this is the result. As you can see, there are some changes between this one before computation and this one after the computation. Therefore, this new table will be broadcasted to the neighbors, which is in this case at T2, we should send this table here to your neighbor, to A, C, and E. And you will do the same computations over and over again. You will keep updating all the time. So now something is really important here, which is how just like this kind of algorithm is converging. So at T0, each router will know its own distance vector table only, right? So this is the first case. I will do my calculations, then since it's going to be a new one, then at T1, C here will just broadcast it to B, because this is the only thing that you can reach, right? Or you have direct link to it. This is at T1. Now, at the same time, at T1, if you look at A, you will do something like this, right? Because A at T0, this is going to be the same thing as what we had before. Now at B, you will have the same thing. Now at this point, C will be aware of A in the next iterations. Therefore, you can see now A, E is going to be connected, because now since I'm going to reach to this one and this one and this one, I have visibility to all of these routers, right? So at T3, you can see the convergence is even more here. So the last thing is you have a full visibility to your network, okay? And the way it's working is, I just like give an example here from C, but it's gonna do the same thing for each one of them, okay? So this is just like a quick comparison between link state and distance vector algorithms. So in terms of message complexity, it depends on, just like when it comes to the link state, it depends on the number of routers do we have. So the complexity here is big O of n to a square here. So this is just like the number of routers. So this is the number of messages. So if we have 3 routers, then the number of messages is going to be 3 to the power of 2. It's going to be 8. Okay, so when it comes to distance vector, the exchange between the neighbors, convergence time varies. So the smaller the network, the less time it's going to take to converge, and the bigger or the more routers you have, the more time you require to converge. So the speed of convergence, this is the second characteristic that you can compare between these two categories. So when it comes to the link state, it's going to be the same thing. It's n square. Just like this is the complexity of this kind of algorithms. When it comes to distance vector, the same thing. It depends on the time, it depends on how big is your network. But one thing that you may encounter here, which is you may end up with some routing loops. So distance vector is vulnerable to routing loops, which is beyond our explanation here. But you should know that distance vector may be just like vulnerable to routing loops and count to infinity problem, which is these known problems in distance vector. So in terms of robustness, link state, if there's any one or any router that advertise incorrect link, then the whole network is gonna be messed up. Okay, because each one is gonna calculate its own table and just like to the other let's say to the other neighbor routers. So when it comes to the distance vector, it's going to be just like black holing. In black holing here, which means I can, as adversary here, I can pretend that I have the lowest cost and share the link between, or let's say share my distance vector with the other machines. So all of them is gonna just like come to me, but never goes out from my router. So let's say that you have router here, router here, router here, and router here. Let's just like give an example about this way. So let's say that you have here 1, 3, 5, 6, and 8. And let's keep this one as 9. If for some reason this one is an adversary and they promote, or this adversary here promotes a distance vector table with least cost, all of the other routers will always forward all the packets to this guy here because he is just like the one that has the least distance vector table. This is why we call it black holing. Everything is gonna be forwarded here, but nothing is gonna go out. Okay, and in case, like in terms of distance vector, if you have any error, then the error will propagate from one node to another. By now, you should be familiar with the routing categories or routing protocols categories that we have, either to have a distance vector based or link state based. The one that we are going to talk about right now is OSPF, which is one of the most common and widely adopted link state protocol. Okay, so before we get into OSPF and how does OSPF work, let's just like make some discussion regarding the routings that we already talked about. So most of the things that we already studied, we assume one thing, which is all the network is flat. That means I have visibility to everything, and this is not the case in the real practice or in real life scenarios. This is not the case. You might have some flat network in your just like internal network, but this is not the case because, as you recall, the internet is just like the internet is networks or network of networks, right? So you cannot have control over all of these things, right? Therefore, we will have tons and billions of destinations. So what we can do, can we store all these destinations? And the answer for sure is no, right? There's no way that we can just like have everything in just like our routing table. This is the first thing, or the first perspective, which is the scalability. The second thing, which is the administrative autonomy. As we mentioned before, the internet is a network of networks. So each network has its own policy, has its own admin that enforce the policy within the network or within the company itself, right? Therefore, we cannot have just like flat implementation. Okay? Now, the internet, how just like to make the internet is more scalable, how to make the routing through the internet is more scalable. So we do something called, or we have something called domains or autonomous systems, where we aggregate the routers into regions. Instead of dealing with each router by itself, we deal with regions. So we group multiple routers into this autonomous system. And we have another autonomous system that has even maybe more. Then we will link or do just like the link between these two routers within each autonomous system here. This is two. So this router here will act as a gateway to this autonomous system, number one. And the same thing for this one. This router here is going to be acting as a gateway for this autonomous system. Okay, so one thing here which is really important for you to understand, which is the intra autonomous system, or what we call it within intra autonomous system or intra domain. This area here, or all this autonomous system, must have some let's say unique, or they have to have some understanding between all these things. All these routers should understand each other. So all the routers within autonomous system must run the same protocol. So if you are running OSPF, for example here, that means this one must run OSPF, this one must run OSPF, the same thing for each one of them. On the other hand, if you want to run, let's say, RIP, for example, as a routing protocol for this autonomous system, each one of them, which within this autonomous system, must run the same routing protocol. That means if you're trying to run RIP in here, in one of the routers that runs OSPF as routing protocol for this autonomous system, you will not be able to do that. Okay? Here, the gateway router is also called the edge, will play a role as the link between or interface between the two autonomous systems. The inter autonomous system or the inter domain, it means we have to have some routing protocols that we can implement here to ensure the packet is going to be forwarded from one autonomous system to another autonomous system. So in this case, let's say that we have these three autonomous systems, 1, 2, and 3. As you can see, 2A here is the gateway of autonomous system 2, right? And 1B and 1C play as a gateway also. This is for this side and this for this side. And the same thing for 3A here is acting as a gateway. So here we can say we are intra-domain routing. And at this point, we can call this inter-domain. Okay, so now, as we mentioned before, all the routing protocols within one autonomous system must be the same thing, right? Let me try to delete this writings. So what do we have in terms of, let's say, if we think about A1C, what do we have in 1C? We should have two main components there. We should have all the routing entries for both, for the intra domain and the inter domain, right? So as you can see here, we will have in forwarding table that we have in this router, for example, we should have the intra autonomous system routing, and we should have the same thing for the inter autonomous system routing. Okay, so this should be all there in the forwarding table for 1C. So let's suppose that any router in AS1 received a message that it's destined to just like one of the routers in AS1, where we should forward it. Right now, this autonomous system has two gateway, right? Should we forward here, or we should forward it to here, right? So at this point, the inter-domain routing must learn which destination reachable through AS2 and AS3, right? That means we have to have a summary of the networks that we can reach within S3 and a summary of the networks that we can reach from 2. So this must be in each of the gateways. It must know which one. Okay, this is the first thing that we have to be aware of. The second thing, which is this information that we get as a gateway, we must broadcast it to the internal routers. So we have to propagate this reachability info to all the routers in AS1. That means if I have something in here and something in there, all the routers within the autonomous system must be aware of the networks. Therefore, we can just like forward the packets in the right way. If we want to send something to, let's say, to 2C here, then we know that it must go through this path. Okay? So some of just like examples of the inter-domain or inter-autonomous system routing. One of them is RIP, which is not commonly used nowadays. Maybe RIP2 might be used in some places, but the original one, it's not as common as it used to be. Most of the time, it's this just like RIP is classical distance vector based, and the distance vector tables is updated every 30 seconds. So as what we mentioned before, it's no longer widely used. So the second one, which was just like Cisco proprietary protocols for decades, also EIGRP is distance vector based. The one that we mostly use and see nowadays is the OSPF, which is based on Dijkstra algorithm, which is link state routing. And there's another one which is ISIS, which is not that just like widely adopted, but essentially it's the same as OSPF, or it's working as a link state routing. So now let's see OSPF. So OSPF is just like classical link state. Each router will float OSPF links state advertisement using the IP. So it's not using TCP UDP. So in this case, we will reduce the overhead of the computations. Okay, and this advertisement should be going to all the routers in the entire autonomous system. OSPF supports multiple metrics that we can see. So if you recall, if we have a link like this, or network like this, or graph like this, we used to have some numerical notation here, let's say 3, 5, and 2. This is, we called it before as a cost, right? So OSPF has multiple metrics. So one of the metrics, which is the bandwidth or the available bandwidth of this link, and the delay we have for the link. So either to work on this or to work on that, or you can even come up with your own implementation. So it's already open source. You can just like work on it. Okay, as what we mentioned before, it's Dijkstra algorithm based. So the same thing that we learned before is applying here. For security purposes, OSPF provide something called authentication, where each router will do authentication. Therefore, we're trying to eliminate the adversary who pretend to be a router. So this authentication must be just like done to be able to exchange the routing table or information that you have on the network. Okay, so OSPF is not let's say flat protocol in nature. That means it's hierarchical in nature, which means each one, or we can create multiple areas where each area will be dealt with as autonomous system. So in this case, all these, let's say in this area or area 1, they must use the same thing to be able to advertise. So the advertisement here scope is going to be within the area only. So if if this router send a broadcast to all the routers here, so the scope of this broadcast will be within the area. There is no other area can reach to this specific thing. So this is the first thing that we have to understand. We can create areas, and we have a backbones that collect among, just like other routers, the gateway for each area. So in this case, let me just like give you a scenario. So let's say that area 1 is marketing department, and this one, let's say finance, and this one is just like the services. And all these areas is connected to the company network. So at this point, you're trying to do some segregation into your network. You are trying to reduce the overhead. You are trying to reduce the broadcast domain for your network. If you have just like everything in here and just like one network, it's gonna be a huge network. It's gonna be too much for the management to manage. But since you just like do some segregation here in your network, you will be able to do it or deal with it as multiple networks. Okay, the last piece of this chapter is how do we route through the ISP or the service provider. Most of the time we are using something called BGP, which is the protocol that it glows or run on the internet. So BGP stands for Border Gateway Protocol, and this is the just like the glue that holds the internet together. So the way it's working is this protocol allows subnets or the networks to advertise its existence and the destination it can reach to the rest of the internet. So that means this routing protocol is designed for just like the internet. So it's based on the internet. The way it's working, each autonomous system, they are going to use or advertise their existence, and the networks that you can or they can just like forward your packet to, right? So the destinations it can reach. Okay, in BGP there are two types of routing. the first one, which is the external BGP, and the other one, which is the IGP, or the internal BGP. Okay, so the external is the same thing as if we have autonomous system here and autonomous system here. The link between these two, we are going to exchange these data using external BGP. Okay, and within the autonomous system, we are going to use IBGP. So the main thing for this kind of protocols is based on how to choose the best or the good path or routes based on two criteria here. The first one, which is the reachability information, which this one each protocol should provide, right? But the other key point for BGP here is the policy. So updating the routing table is done based on the policy that you are using. So maybe if you have autonomous system here and autonomous system here and autonomous system here, and you share the network, maybe based on the policy, your network will be accepted, but in the other network might not be accepted based on the policy used for that specific autonomous system. Okay, so as you can see here, the link or the communication between two autonomous systems is using eBGP, and within the autonomous system we are using the IBGP or the internal BGP. So as you can see here, for autonomous system 3, 2, and 1, we have this one as a gateway for autonomous system 1, and for autonomous system 2 we have two gateways, one here which is A and the other one which is C, and for this one is going to have just like only one gateway. So most of the time BGP, the session of BGP, it will just like create a semi-permanent TCP connections, and through these connections you will advertise the path, or the path is the different destination of the network and prefixes. So BGP is a path vector protocol, so it's all about path, what you can reach, what you cannot reach. So for example here, let's say that X is part of autonomous system 3. So A here is going to advertise or send advertisement here to the neighbor at this point. 2C is the neighbor. It's saying that to access X, it must go through autonomous system 3. This is the way it's working. Now, when C here receive this advertisement, it's gonna process it or just like do or apply the policy within autonomous system 2. If this one is fulfill the policy or accepted by the policy, then it's gonna be broadcasted to all the network here, to this one, to this one, to this one, through IBGP, and it's gonna be broadcasted to this one here through eBGP. Okay, so this is the way it's working. So what are the prefix here and what are the attributes? So the attributes here, so there are two important attributes. One as path, which is list the autonomous systems that you can just like reach. Let's say if we have this autonomous system here and this autonomous system here, let's call this one AS1, AS2, and this is AS3. Once, let's say the path advertised from here to here, let's say X and AS1. This one, the advertisement, right? So when the gateway here is going to advertise it, it's going to do AS1, AS2, then X. So it's saying to access X, you must go to AS2, then AS1, then X. And the other thing which is going to identify here, which is the next hop, which means indicates the specific internal AS, so the next hop within the autonomous system. Okay, so as what we mentioned before, BGP is policy-based routing. That means whenever you receive advertisements, you will apply the policy. Based on the policy, either to accept that specific path or advertised path, or you may decline it, as what we mentioned before. Okay? The other thing that policy define here, other than accepting or declining any path, is gonna tell or determines whether to advertise the path of the others or not. So we can say that the policy is the regulations of the gateway there. Okay, so let's say that X here is part of autonomous system 3. So 3A here is going to advertise this message, which means X is part of autonomous system 3. So once this message is received by 2C here, it's going to do two things. The first thing, for sure, after applying the policy, let's assume the policy is advertise whenever you have, accept everything whenever you have, broadcast to everyone, and you will just like share it with the other autonomous system. So in this case, you will do, or let's say 2C is going to do BGP exchange with all the other routers, with this one and this one and this one, right? The other thing that it's going to do is going to instruct 2A to advertise this message or this path to autonomous system 1, as you can see. So here, AS2, AS3, and X. That means if this router here wants to send a message from here to X, that means you have to send it to the gateway of my autonomous system, which is connected to autonomous system 2, and from here I can forward to here. Once it's arrived here, then I can just like access it from here. So this is the way it's gonna work. Now, what if in this case we have another link between autonomous system 3 and 1? At this point here, we'll be able to see that we have two paths. Based on the policy here, you will be able to choose which one to go with. Okay, so it depends all on the policy. Okay, so for this example here, autonomous system 1 get from 1C that this path, right? This is the one. And from 3A, it got AS3 and X. Based on the policy, as what we mentioned before, 1C, it shows this path based on the policy. Maybe in the policy we are saying the least, or let's say the least hubs, for example. So it depends on the policy, okay? But at this point, 1C should do one really important thing, which is should broadcast everything to the other routers. That means every router within autonomous system 1 should be aware how to reach to router X. So the kind of messages or the type of message that we have with BGP, we have four main messages. The first one, which is open, which is going to open the TCP connections to another BGP router. Update message is used to advertise the new path or even drop one of the previous ones. Keep alive is to just like a signal. It's like a signal message to keep the connection alive in the absence of update. That means if you have two routers here, you don't want to close this connection, so you won't need to establish a new connection. This is just like used as a signal, not to close the connections. Notification here is when you want to report error in the previous messages. In addition, sometimes we use it as a close connection message. So this is just like one example here, which is if you try to examine the routing table here, you will find that 1C, you can use the interface number 1, right? And the same thing, if you wanted to access X, you will go through 1C, because every one of them, each one, should have the same entry here, right? So here it should be going out this way. Therefore, we are using this output. So if we are using, let's say, the other one here, which is this one, so 1C, we can go through the interface number 2, which is this one. Okay, the same thing is going to be X should be forwarded through the output or the interface number 2. So why different intra and inter autonomous system routing? Why do we have to care about this? Why it's working differently? Why do we have multiple routing protocols? So most of the time, we have some criteria or some features that we are looking for. So when it comes to the policy, the inter-autonomous system admin wants to control over how a traffic is routed. So for me, as a policy, this is some regulations, how the network will be functioning. On the other hand, the intra-autonomous system is one single admin, so the policy here is not a problem because you are the one who created the policy. But within the inter-autonomous system, it's going to be not your policy. So you cannot enforce a policy that is not yours, right? So the other thing here, which is scale. Hierarchical routing saves and reduces the table size. And whenever you reduce the table size, that means you reduce the update traffic. So you don't need to do that many updates on the traffics. The performance, most of the time, the intra-autonomous system can focus more on the performance, where the, let's say, the inter-autonomous system will focus more on enforcing the policy. Okay, so as what you mentioned here, in the intra-autonomous system, we are focusing on more on performance. In the inter-autonomous system, we are focusing more about enforcing the policy. So this is just like one another example for distance vector. You can just like go over it on your own. Thank you.